Now that we've had a chance to talk about the sum and difference identity for cosine, we're going to tackle in this lecture the sine sum and difference as well as the tangent sum and difference. So let's just start out, and I want to remind you that we had the cofunction identity, which said if I took the sine of theta, that was equal to the cosine of 90 minus theta. Well, let's just suppose that we want to let theta be equal to a plus b, where I'm adding two angles a plus b. So I could rewrite the left-hand side here so that it looked like the sine of a plus b, because I'm substituting a plus b in for theta, and I'm going to rewrite that on the right-hand side over here, the cosine of 90 minus a plus b. And I think I'm going to simplify the information inside of this parenthesis, so it becomes the cosine of 90 minus a minus b. Well, I know from the cofunction identity, again, that I can rewrite that maybe I want to look at something so that it looks like 90 minus some angle, 90 minus a in this case. So I'm going to group, in other words, this so that it looks like 90 minus an angle minus b. Okay? So, having done that, all I did was really use the associative property to regroup what I had already inside of the parentheses. Remember from the last lecture that we talked about the difference identity for cosine, and that's what I have here. I have some angle here minus another angle here. So we're going to apply the difference identity for cosine, and it says the cosine of the first, which is 90 minus a, times the cosine of the second plus the sine of the first, 90 minus a, times the sine of the second. Okay? Now, I know that the cosine of 90 minus a, right, the cosine of 90 minus a is equal to sine. Sine of a is equal to the cosine of 90 minus a using the cofunction identity. So I could rewrite this portion right here as the sine of a times the cosine of b, and I can apply that same property, the cofunction identity over here, where I'm rewriting this in terms of cosine using the cofunction identity, and that becomes the cosine of a times the sine of b. Now what I've done basically, and I have to stop there because I can't do anything more, what I've done basically is using the cofunction identity that we're already familiar with, I derived the sine sum identity. Okay, so that's the algebra behind it. I think it's kind of interesting to look at that. And now what I want you to do is I want to make sure that you write down what I just derived. This is the sum and difference identity for sine. It breaks up into the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second, and then you can see there what it looks like when we talk about the difference. Okay, so if we know that that is now going to be added to our list of identities that we're keeping, let's come down here and let's look at this first example. The first example that we're going to use says I want to find the exact value of this expression. In other words, if I know the sine of 15, can I come up with two angles that either I add together or subtract from each other and get 15 so that I can apply the sum or difference identity for sine? Well, I'm going to say that 15 is equal to 45 degrees minus 30 degrees. So remember, I'm choosing angle measurements that exist already on my unit circle because I can take the sine of 45 and get an exact value. I can take the sine of 30 and get an exact value. So that's why I chose these two values here. as I think we've proved before, it doesn't matter if you use these two angles or any combination of angles from our unit circle, as long as they come up with 15. So let's apply that. So we're going to go through and we're going to say the sine of 45 minus 30. So we're going to use the difference identity for sine. That one looks like the sine of the first, so the sine of 45 times the cosine of the second minus the cosine of the first times the sine of the second. So we put it in terms that I can now find exact values of. Well, the sine of 45 is going to be the square root of 2 over 2. The cosine of 30 is square root of 3 over 2, minus the cosine of 45, which is the square root of 2 over 2, and the sine of 30, which is 1/2. So we have this expression here now that we're going to simplify. I know that square root terms are like, so I'm going to multiply them. They're similar, so I can actually multiply them together. So I end up with the square root of 6 over 4 minus the square root of 2 over 4, which I'm going to rewrite as a single fraction. So it's the square root of 6 minus the square root of 2 over 4. Again, I cannot reduce this fraction because there are no numbers or no values on the outside of my radical sign for me to reduce with my denominator. Okay, so there's the answer. That's what we got right there. The sine of 15, the exact value of the sine of 15 is going to be the square root of 6 minus the square root of 2 over 4. Let's try that again. This time I'm going to use the sine of negative 105. Now I'm going to challenge you. I want you to stop the video and I want you to come up with this problem on your own and then come back and let's see if we got it together. Okay, so I went ahead and I worked the problem with two angles that added together to give me negative 105. I chose negative 60 and negative 45. And when I worked this using the addition identity for sine, then I come up with an answer that says negative square root of 6 minus the square root of 2 all over 4. So what angles did you use? Maybe when you stopped the video and did this, maybe you did this a different way. Maybe you said that negative 105 could also be equal to a positive 255, and you chose angles that added together to give you 255. Maybe you chose 225 plus 30. Maybe you chose 210 plus 45. I don't know. As long as whatever your measurements are, right, you're choosing measurements off the unit circle that either add or subtract to give you your original angle value. In this case, I took the negative and I changed it to a positive angle, and we can come up with these values here. It shouldn't matter. It shouldn't matter if you used these values I chose or these alternate values, which are just some in a long line of values. Ultimately, your final answer should still look like this. So it doesn't matter which you choose. Okay, well that's the sine sum and difference. Now let's look at what the formula says for the tangent sum and difference. Take a minute, write down these two identities that we have going on here. The tangent of a plus b breaks into the tan of a plus the tan of b, divided by 1 minus the tan of a times tan b. And then you can see over here what it is for the difference identity. Well, let's go using the same concept we just practiced with sine, and let's apply this using tangent. So again, I'm going to choose angles that add together to give me 105. I happen to choose 60 and 45. Angles that exist already on the unit circle. So when I do this and apply it using the sum identity for tangent, it breaks up into the tangent of the first plus the tangent of the second divided by 1 minus the tangent of the first times the tangent of the second. Okay, so that's how it's going to expand out. Now let's go replace the tangent of 60 with what I know it is off of the unit circle. Okay, I know that the tangent of 60 is going to be the square root of 3. The tangent of 45 is 1. So I'm going to use those same values, and I say 1 minus. The tangent of 60 we already said is the square root of 3, and the tangent of 45 is going to be 1. So square root of 3 times 1 is just the square root of 3. Well, I'm not done there because I have to get rid of the denominator. In other words, I don't want radicals in my denominator. So maybe you remember, maybe you don't, but in order to do this, I'm going to multiply by what we called the conjugate. Okay, the conjugate of the denominator looks like the same thing, 1, only I'm going to use the opposite sign, so 1 plus the square root of 3. So I multiply top and bottom by 1 plus the square root of 3, and I'm going to FOIL that, numerator to numerator. In other words, I multiplied this binomial by this binomial in the numerator, and then I multiply the same thing, same concept in the denominator. So first outer inner last, right? So I take the square root of 3 times 1, which is the square root of 3. The outer terms, which would be just 3. The inner terms, which is 1. And the last terms, which is the square root of 3. Then the denominator, again, becomes the first term. The outer terms, that's a plus square root of 3. The inner terms is a minus square root of 3, so they cancel. And the last term would be minus 3. Now I need to simplify my numerator and my denominator. So this square root of 3 and this square root of 3 are what we would consider like terms. So how many of those do I have? I have 2 square roots of 3. And then this 3 plus 1, those are like terms, so that becomes 4. The denominator is negative 2. Now I can simplify this fraction, okay? I can simplify it because I can look at it in terms of one fraction and a totally separate fraction. Let me rewrite this, broken apart as 2 separate fractions. It's going to look like negative 2 square roots of 3 over 2. And then we're going to just use that as minus 4 over 2. Okay, so all I did was take this fraction here and break it up into 2 separate fractions. And you can see that I can reduce, now that I have it broken up, I can reduce because this 2 is going to divide into that 2, or I can divide the top and the bottom by the same number, I should say. And I'm going to get negative square root of 3, and 4 over 2 is just 2. So this is what my answer should look like. This right here. Let's put a circle around it. Okay, so tangent isn't really that difficult to set up, but because it has a fraction in it and we usually end up with radicals, we're going to have to do this rather more complicated step. Let's look together then at this next example. This next example says I want to find the tangent of 13 pi over 12, and I want to find the exact value of it. So I'm going to think to myself, I want to look at my unit circle. So let's go look at the unit circle real fast. I'm going to pull it up for you. Okay, so here I went ahead and pulled up from our previous notes our filled in unit circle. And remember that I am actually looking for 2 angles that are going to add to get together to give me, what was it, 13 pi over 12. Okay, well, in order to add my fractions or subtract my fractions, I have to have a common denominator. So I would need to convert or rewrite each one of these fractions as an equivalent fraction with a denominator of 12. I don't really want to do that for all of these numbers. So let me give you kind of a strategy that I tend to use when I'm trying to figure out what these two numbers would be. I know that I'm looking for two things that are going to add together to give me 13. So I'm just going to start with some numbers. I know that 8 plus 6, no, I know that 6 plus 7 add together to give me 13. I know 10 plus 3 add to give me 13. I know that 5 plus 8 add together to give me 13. Well, if that's the case, then each one of these would have to have a denominator of 12. So if I were looking at this pairing right here, I would have to be able to find an equivalent angle off of the unit circle that would be the same as 7/12. Well, there is nothing on here that's going to give me 7/12. So this one I can cancel. How about this? 10/12 and 3/12. That one's looking more promising to me because if I reduce 10/12, then that really gives me, what, 5/6? And 3/12 reduces to be 1/4. Well, 5 pi over 6 exists, and pi over 4 exists. Okay, so this would actually be the angles that I'm going to utilize off of my unit circle. Okay, so that's kind of my strategy for being able to do this. So let's go back to our other notes using 5 pi over 6 and pi over 4. So remember, we're saying that we can use the tangent of 5 pi over 6 plus pi over 4 because those two fractions add together to give me 13 pi over 12. All right, so let's apply that. We know that that's going to be the tangent of the first plus the tangent of the second divided by 1 minus the tangent of the first times the tangent of the second. So now that we've simplified that, or expanded it out, I guess, we need to go in and simplify what the tangent of 5 pi over 6 is. Well, the tangent of 5 pi over 6, if you have your unit circle sitting out in front of you, or if you've memorized it already, you should remember that the tangent of 5 pi over 6 will be negative square root of 3 over 3. The tangent of pi over 4 is just 1. Okay, so then we rewrite the denominator as 1 minus a negative square root of 3 over 3 times 1. So I'm just going to leave that off. So this is going to get rather complicated. Let's simplify the denominator. In other words, make this, I'm going to rewrite the numerator as that, and make this 1 plus the square root of 3 over 3, because we would normally have to change. Okay. Well, remember I told you that you cannot have a radical in the denominator, so we would need to multiply the top and bottom by the conjugate. So the conjugate is the same thing with a different sign. So it would be 1 minus the square root of 3 over 3 and 1 minus the square root of 3 over 3. Now we're going to FOIL. In other words, we multiply the numerators together. When I do that, I end up with negative square root of 3 over 3. Now, negative square root of 3 over 3 times negative square root of 3 over 3, right? That's going to give me 3 plus, it's going to give me 3/9, which reduces to be 1/3. Now let's do 1 and then minus square root of 3 over 3. Okay? So the denominator, since these have opposite signs, this becomes the square of the first minus the square of the last, which would just be 3/9. Okay? Now, 3/9 and 3/9 reduce to be 1/3. I'm going to reduce those. Okay. Let me rewrite this so it's a little cleaner now. So this becomes negative square root of 3 over 3 and a negative square root of 3 over 3. So I have a total of 2, negative 2 square roots of 3 over 3. Now this right here, I'm going to add 1/3 plus 1. And I'm going to leave it as an improper fraction. 1/3 plus 1 would be 4/3. The denominator, 1 minus 1/3, is going to be 2/3. So I end up so far with this right here. Now this is what we would call a really complex fraction. And there's a trick to be able to get rid of these denominators, or to get rid of that so that it looks a little cleaner. Notice that all three denominators for these fractions are the same. So if I were to multiply the top and the bottom by this common denominator of 3, then it's going to have the effect of getting rid of these fractions. So if I multiply the first term times 3, let me just do that over to the side so you can see what's happening. Okay, so this is really like saying negative 2 square roots of 3 over 3, and I want to multiply that by 3, which I have to rewrite as 3 over 1 because it has to be as a fraction. So remember, I'm only multiplying things that are in the numerator, and this 3 that we're considering in the numerator is like this 3 over 1. Well, notice what happens when I do that. The diagonals are going to cancel, and it just leaves me with this negative 2 square roots of 3. That was the goal, right? I wanted to turn this fraction into a whole number. So when I multiply 3 times 4/3, those 3's cancel and I'm left with just a 4. And the same thing happens down in the denominator. 2/3 times 3 just gives me 2. So this ugly looking thing turned into this, which is at least a little bit better. And again, I can reduce this fraction because this 2 divides into that 2, and this same 2 divides into that 4. So as long as it divides into both terms, the same number divides into the both of the top numbers, then I can reduce this, and this becomes negative square root of 3 plus 2. Oh, that's pretty complicated, that complex fraction right there. We're going to see this again later on in the next lecture, same lesson, where we use this property again. So remember it, okay? Now the last example that I want to work in this video looks like this example here, okay? And this is the same the same instructions that we've been finding so far. I want to be able to write this. I want to be able to find the exact value of this expression. Well, notice here that I have 100 degrees and 70 degrees. Okay, so I'm only dealing with two angles here, and it's the tangent. Okay, so we're going to use our new identity that we talked about today, which was the tangent of, because the numerator is negative, this would be the difference identity. So it's the tangent of 100 minus 70, because those are the only two angle measurements I'm using in this example. So let's simplify that. That becomes the tangent of 30. Well, the tangent of 30, this is going to be easy, is just the square root of 3 over 3. So that was a whole lot easier than the previous example, but I wanted you to be able to see how I can kind of go about this backwards. I took the identity in an alternate form, rewrote it as the difference of just two angles, simplified it, and I'm done. All right, that's the end of this particular section.